Good afternoon, everyone. Thank you for joining us. And today, as the title says, we'll talk about the basics of seismic interpretation. And in the next number of lessons, we'll get into more details on some of these different interpretation methodologies that we use. So in lecture 6, we talked about what generates reflections. We talked about impedance, which is the density times the velocity. We talked about how we calculate reflection coefficients that tells us what percentage of the energy is reflected at each of the acoustic boundaries. Talked a little bit about the mathematical operation called convolution, so that if we know or can assume what the pulse is that we send into the ground, we can convolve it with each of the individual reflection coefficients, and that gives us the idealized trace. So we won't get into any more geophysical theory today. We have looked at the theory, and if you have missed some of the previous lectures, you can take advantage of the repository on the IRIS website or on YouTube. And so we're ready to start to mark our seismic sections. Our first overall goal in doing interpretation is to develop a geological framework. And by that I mean we want to identify and map and correlate the significant fault planes. We also want to look for the most significant stratigraphic surfaces, unconformities, depositional sequence boundaries, and we want to have proper geometries so that when a horizon is intersected by a fault or one fault is intersected by another fault, those intersections are properly displayed. We don't have overlaps or gaps. So in the interpretation process, we should have in our brains basics about the theory behind reflection seismology. Then we're going to be interpreting the faults, and we're going to be interpreting the major stratigraphic surfaces or horizons, and we do that iteratively. So a good seismic interpreter will be at least competent in interpreting faults and competent in interpreting horizons. Many times interpreters in their first maybe 4 or 5 years might be more structurally oriented and not as competent with the stratigraphy. Similarly, there might be a new seismic interpreter that's more competent with the horizons, less competent with the faults. But after about 5 years of doing seismic interpretation, people develop enough of a skill set and experience set that they're at least competent in both. And if we develop a series of the major faults, a series of the major horizons, that leads to the geological framework that we want to establish. So the geological framework, we use all the available data. We may have wells. We should have seismic data. We may have outcrops on the edges of the basin that we're looking at. We may have had regional studies done either by our own company or has been published or available through academia. There are gravity studies, magnetic studies, and whatever other information would impact understanding the geological framework. And we'll build a framework of present-day structure and stratigraphy. And so there's two main components of that geological framework: the structural interpretation, looking for faults, folds, areas of subsidence and uplift, figuring out structural trends and structural features. And then the other half is the stratigraphic interpretation, mapping the main stratigraphic unconformities, the other major stratal units such as depositional sequence boundaries, trying to figure out environments of deposition, what sort of lithofacies we have at different locations, and what sorts of lithologies. And if we don't have well control with paleontologic ages, we sometimes use the seismic stratigraphic interpretation to predict geological ages ahead of the drill. So we want to worry about the structure. We may note a series of faults. We may have folds. We may have diapirs. This is a salt diapir. We can also get shale diapirs. And this is a detached glide plane listric normal fault, reverse a normal sense of offset. When we're interpreting structure, we'll make our observations based on the seismic displays that we're looking at, profiles or time slices. And we'll also have in our heads the structural concepts that we learn in Structure 101, Structure 201, Structure 301, and so on and so on and so on. And as people do more and more interpretation, they're going to build up their own repository of structural information and ways in which to interpret the structure. For the stratigraphic analysis, we'll look for evidence for erosional truncation, such as this level in the upper left. We can look for patterns of discordant reflectors. We have dipping reflectors down to the right, and then almost horizontal reflectors. We call these onlap terminations. We'll talk more about onlaps in a later lecture. We can look at reflection geometries. Here we have a geometry showing a progradational deltaic style of deposition. And then we can look at attributes such as the amplitude along a particular horizon, the higher amplitudes being the reddish brown, the lower amplitudes being the greens and the blues. In interpreting the stratigraphy, again, we'll make observations by looking at the seismic data, and then we have stratigraphic concepts, depositional models that we will use in order to understand what those observations are telling us. One of the things that we commonly generate when we're working on a structural framework are structure maps, and these could be either in feet or meter, true depth maps, or they may be in two-way travel time if we have not yet converted from two-way travel time to depth. So this is an example. This is from the shelf of Louisiana. The colors here represent the two-way travel time, TWT, for the top of a particular sand. The shallow depths or two-way times are in the hot colors, the reds, and as we go into the orange, yellow, green, blue, and a little bit of purple, we're getting deeper and deeper and deeper. We can see on this map that we have a number of major faults, the yellow fault, the white fault, the blue fault that splits, and the magenta fault. But we also have a number of smaller offset faults or minor faults. So the remainder of the course, the various lectures 12 through 33, we'll talk about what happens in the interpretation in terms of developing this geological framework. So we'll be talking about mapping faults, mapping horizons, and then how we use the geological framework for prospecting or for exploration. So the focus of the rest of the course is a little bit lean towards exploration as opposed to field development or field production. But a lot of the interpretation methods that I'll be talking about can be used not just in exploration, but can also be used in development and in production. So given the scope and time constraints of the series of 34 lectures, we'll look at many of the interpretation concepts and procedures and tools, but we won't be able to look at everything that people in industry are doing these days. So if we're talking about exploration, one of the things that we want to accomplish first is to develop the geological framework, the major faults, the major horizons, all consistently interpreted. Then we'll do data analysis. Then we'll examine different prospect elements. And if you missed, I think it was lecture 2, the prospect elements are source, reservoir, trap, seal, and migration. And then if we find a prospect that might be worthy of drilling a well, then we're going to have to do an assessment of the prospect. Is it likely to have oil or gas? And what volume of recoverable oil in barrels or gas in cubic feet do we expect to have? One of the main things we do in seismic interpretation is what we call tying loops. And we want to get a consistent horizon in three-dimensional space, whether we're working with a 2D grid of seismic lines or we have an actual 3D volume of seismic data. This loop tying process started back in the old days when I was young, when we only had 2D seismic lines, but some of the methodology has carried over into interpreting 3D seismic volumes as well. We have a lecture coming up. I don't quite remember the number or the date, but it focuses in on 3D seismic interpretation, some of the things that we can do beyond what we were able to do with only 2D seismic. So what we'll do is we'll interpret faults and horizons along one section. So let's say we interpret line 1, then we'll transfer the interpretation at an intersection. So maybe we'll transfer the interpretation on line 1 to line B that cuts it at 90 degrees, then interpret line B. Then we'll look at the intersection of line B with line 2, copy our horizons and faults, map the horizons and faults on line 2. And then we'll look at line A. Perhaps we'll take our interpretation elements off of this intersection. We'll interpret this line, and then we'll check to see if all the interpretation elements, the horizons and faults, are consistent, have the same two-way travel time at the intersection point. And so if we do any closed loop, and all of the interpretation elements, the horizons and faults, are consistent, then we say that we have tied the loop. Then we could start working on line 3 and close this loop. Then we could work on line C, close this loop, and then finish interpreting line 3 and close this loop. And so this loop tying method is our way to make sure that spatially everything is going to be consistent, that the faults make sense in three-dimensional space, and the horizons make sense. And I'll show an example of loop tying here in a few minutes. So let's loop tie a fault. This is a data set. This is the Basemap. On the right is line 103, which is the line with the magenta. And there is a fault right there. You can see that this white, black, white is probably equivalent to this white, black, white. And we can see in the area where the red line is drawn that reflectors that are on the one side are disrupted and the reflectors on the other side are disrupted. And so we can put a fault through there. The imaging isn't perfect, so we could argue whether the red line should be a little steeper or a little gentler, but it seems to me at least quite apparent that there is a fault offsetting the stratigraphy at about that location. So that's line 103. Now we'll move up to 102, a little bit to the north, and that's where I think fault A is located. So now what we can do is we can take line 103, our first interpreted west to east line, and we can look at where it intersects line 201, the north-south line. So line 201 south to north, 201 intersects at this location, so there should be fault A at that intersection point. So what we do, at least in the old days with paper sections, we would fold the section. We would then slide it to the appropriate intersection point, and where the red fault intersects the line 201, we put a dot. Then we can look at line 102, the second east-west line that we looked at. We can fold it at line 201, slide it over to the appropriate intersection point, and put another dot. There's my cursor. Now we can look at line 201. We have a fault intersection at this position on line 103. We have a fault at this position on line 102. And so we can interpret line 201. And by making sure that at the intersections, the fault has the same two-way time, which is a proxy for depth, we are ensuring that our interpretation is spatially consistent. We can keep track of our interpretation using a base map, either paper or on the computer screen. I first interpreted line 103, then I interpreted line 102, then I looked at 201, and I can put a symbol here, a red circle, to indicate that the fault A is tied, has the same two-way time value at this intersection, and it also has the same time value at that intersection. And so we can work around the grid, building out from a starting point and making sure that all of the faults that we are mapping are areally consistent. Most people working these days do interpretation on computers. This photo's from probably about 1995, plus or minus, and you can see the monitors here are really big beasts, and they generated an awful lot of heat. These days we have flat screens, and it doesn't take up as much space and doesn't generate near the amount of heat that these monsters used to. Typically, interpreters use 2 or 3, and sometimes people use 4 monitors on their desk. One would be for the seismic displays, vertical lines or slices. The other would be Basemap, and the software allows you to use the Basemap to pick different lines that you want to display on the opposite screen. And you can also have interactively updated base maps that show the extent that you've interpreted fault A or horizon W. So let's do a loop tie with a horizon. We'll start with line 103, west to east, line 103. Here's the fault. There is a major unconformity about a quarter of the way down. You can see above the yellow line, things are fairly horizontal. Below the yellow line, things are dipping up to the right. And so there was a deposition of the older material. Then the faults moved. We had some tilting and then some erosion. And then we had post-fault movement deposition of the material above it. So we've interpreted line 103. We can take line 103 and let's look at where it intersects line 204 at this position. Here's line 204. Here's where line 103 intersects. So again, I can fold the paper. I can slide it over. And now I can transfer the interpretation from the east-west line 103 to the north-south line 204. Then I can take line 103 away, and I can complete the interpretation of line 204. So I started with line 103, then I used that to get the interpretation on line 204, and I completed the yellow horizon on line 204. Here's line 102, just to the north of 103. Now I have the interpretation on line 204 at the intersection point. So I can fold one and slide it over, transfer the interpretation from line 204 to 102, and do the interpretation. Then I can take line 102 and interpret it further to the east. And so now I've interpreted 2 east-west lines, 1 north-south line. Let's look at one more north-south line, line 201. Here's line 201. The intersection point is here and here. So again, I can fold the paper, slide it over, and interpret the uninterpreted line north-south 201. Then take the east-west line away and complete the interpretation. Now is the test to see if all of this is area consistent. I can now look at where 103 and 201 intersect. That will complete this loop. And so again, I can fold the paper, slide it over, and does the yellow horizon on each of the two displays have the same two-way travel time within the accuracy of me using PowerPoint? Yes, they do. And so the yellow horizon is aerially consistent around that closed loop. Then I can work on other lines and close more loops and bootstrap myself around and get the yellow horizon on every line. I've been talking about folding paper sections. We can do the same essential process these days on computers, and it makes it a whole lot easier to let the computer handle the intersections than us to manually fold paper and slide it around. So if you remember our goal, the first step is to build the geological framework. That's to build the structural framework, the main faults, to build the stratigraphic framework, the main horizons or sequence boundaries. Then we want to identify our prospect elements: source, migration, reservoir, trap, seal. Where are all 5 of these elements favorable? That would be where we would want to focus our exploration efforts. We have to assess the highest potential prospects. How much oil or gas do we expect? And how certain are we? How risky is it? Or what's the chance of success? And then if it looks like it would be economically viable prospect worthy of a exploration well, then we'll have to do an economic analysis, try to figure out what the volume of the hydrocarbons are, or the oil and or gas, how much money that would equate to when we sell it, and subtract that proceeds from the sales of the hydrocarbons from the total cost, and that would give us an estimate of what the profit would be. So that concludes my prepared statements. We are finished the first column, so almost a third of the way through the course. On next Tuesday, we'll talk about new ventures. And then next Thursday, a week from today, we'll talk about prospect mapping. And I said 3D seismic interpretation, that's lesson 19. If we don't have a bump in our schedule, that I'll cover on August 31st. So I will turn it back to Dr. Sumi and see if there are any questions.
Okay, great. Thank you, Fred, for that webinar. I'll give everyone a second to write in their questions if there is any. Okay, we did have one come in. So Norman Zeb asks, if we have formation tops, is it possible to mark horizon without well tops?
If I have the question correct in my mind, okay. Saying we have wells with formation tops. Mm-hmm. And what we'll talk about on August 17th is well seismic ties. How do we take our well information, including formation tops, and figure out what that represents on the seismic in terms of a particular peak or trough or zero crossing? So yes, we can merge the seismic with the formation tops as picked by a geologist using well log information.
Great.
And if that's not quite the question that we can try again.
That's right. Yes, he wrote back in that yes, that was it.
Good.
Okay, well, I'll wait another minute to see if there are any more questions. But with that, it's a quick webinar today.
Yeah, it's a kind of an overview, and you know, some of the lectures are a little shorter, some are a little longer.
They're good. That's good. So I don't see any more questions that have come in. So with that, oh wait, More just came in. Okay.
I might make a comment. August 22nd, the title of the lecture is Seismic Acquisition. I think some of the information went out. It said it was building a fold map, and that was the title of the exercise.
Okay.
So August 22nd, we'll be talking about seismic acquisition.
Right. So that is changed in the webinar.
Seismic.
Yeah. Okay. So we did, oh man, okay. Some complicated names, so I'm not going to try them. But how do you analyze seismic interpretation uncertainty?
The uncertainty, yes. As you'll see, as we get into the interpretation, there's a lot of decisions. I showed fault A with the red line, and I said you could make it a little steeper or a little gentler. And so there are thousands, maybe hundreds of thousands, maybe millions of these little decision points that interpreter will make as they're developing the geological framework. And so management is aware of the process and the fact that there's a whole lot of decisions that are made. One of the ways that we check and try to eliminate false interpretations is to do the loop tying and make sure everything makes sense in 3 dimension. If we have 3D seismic data, we can use 3D volume interpretation displays to help make sure that everything looks geologically reasonable. The ultimate decision whether something is worth drilling or not will depend on the size of the reserves, oil or gas that you think you're going to recover. And so one of the ways they handle uncertainty is by trying to get the most likely or best educated guess values. And then what if I'm a pessimist, if some of these things are less than the best case scenario? And then we do the optimist case, what if it's better? And so we'll give management at least 3 answers to how much oil they might be able to recover. And management then will use that to try to balance the risk versus the reward.
Great. We had a question that came in that said, what if the ties are not consistent or the reflectors are not matching?
Could you repeat that for me?
Sure. What if the ties are not consistent or the reflectors are not matching?
If the horizon isn't consistent or the horizon isn't consistent at an intersection point, then it means you have a bust in the correlation. So at any XY lat long, unless we have a really complicated fault, each fault should have only one value. And unless we have reverse faults, each horizon should have only one value. And so if you check an intersection and the 2 views of the horizon or the 2 views of the fault are not consistent, then it means that you have to do some editing of your interpretation. Typically what people will do, let's say we're working on fault A, we may be looking at some lines that are more in a structural dip orientation, some in more of a structural strike orientation. They'll put more weight on the interpretation on the structural dip oriented lines and then adjust the interpretation on the structural strike orientation so that it becomes more consistent.
Okay, great. So that's all the questions that we have today. So, oh wait, one just came in. Okay, so what are the points that we need to keep in mind to choose positive or negative phases to picking?
Again, can you repeat that? There's some static on my phone.
Oh, sure. Okay. What are the points that we need to keep in mind to choose positive or negative phases to picking?
Positive, negative phases. I am thinking that that, in my terminology, would be peaks or troughs on the seismic. If we have well data and we're trying to map a formation top or an age boundary, we can use the well seismic tie methodology, model trace or synthetic trace, in order to understand, is the top of the Austin chalk going to be a peak or a trough? Is the top of the Wilcox going to be a peak or the trough? Is the top of the Latrobe going to be a peak or a trough? If we don't have the well information, we'll use evidence on the seismic, primarily reflection terminations, to try to figure out where the significant stratal surfaces are, whether it's in a particular peak or a particular trough. And if we're dealing with zero-phase seismic, which is normally the standard, the horizons should be centered on peaks or on troughs, not on zero crossings.
Okay. We have another question. Where do the faults have steeper dips in seismic, at the dip line or strike line?
Again, can you repeat that?
Where do the faults have steeper dips in seismic, the dip line or strike line?
I hear the dip line and the strike line, and I'm not sure what the question is about. Again, the static is hurting.
Copy and paste it into the chat.
Okay. Oh, okay. The faults will be steeper in a structural dip orientation than in a structural strike orientation. The strike orientation, the fault plane can be almost horizontal if it's a pure strike orientation. One of the great things about 3D seismic data volumes is that once you know approximately what the orientation of the fault is, you can select lines that are pure structural dip or pure structural strike or anything in between. If we have a 2D grid of seismic, the orientations that we can look at in the fault are predefined by where the 2D lines actually are positioned.
Okay, well, great. So that's all the questions that we have. Thanks to everyone who tuned in, and thank you for your wonderful questions. And thank you, Fred, for your presentation. I appreciate it. And we will see you all next week for the 2 lectures on new ventures and prospect mapping. So, all right, well, have a good day, everyone. See you next week.
Hey, thanks for everyone tuning in.
All right, take care. Bye.
Hey, bye-bye.